So you don't believe in God.
What you have to realize is that science today operates under what we call methodological naturalism.
Evolution does not work, no matter how old the universe.
I want to start off with the question, what was the best book or article that you have recently read? Who was it written by, and what was the storyline? How did it draw you in and make you think about what the author was saying or how the characters were interacting? Maybe you are an art buff and you love art. And think about something that you have recently seen, maybe a classical piece that is your favorite. You've seen pictures of it on the internet or on a TV program. Maybe there's a local artist right here in the vicinity that you were able to appreciate and see what they did. I want you to think about what that characteristic of that piece or that book that kind of made the connection with you. And I want you to hold on to that thought just for a moment. In 2003, there was an exchange between James Watson, the co-discoverer of the shape of the DNA helix, with a student at Youngstown State University. And the student asked James Watson, said, "So you don't believe in God?" Now, this was after a lecture that Dr. Watson had presented, and there was a question and answer period, and the student, from what was being said, asked this question, "So you don't believe in God?" And look at Dr. Watson's response. He said, "Oh no, absolutely not. The biggest advantage to believing in God is you don't have to understand anything. No physics, no biology. I wanted to understand." Now think about that statement for a moment. This statement is sometimes classified the God of the gaps. And what Dr. Watson is saying is, he's saying that if you believe in God, then you have set aside all of the rationale. You've set aside all of the reasoning power, the logical understanding for what is around you. He said, if you believe in God and you take on religion, then you set aside any endeavors for science. And he said, I don't want to do that. The fallacy to this is the fact that he is saying that faith in God, faith in the Bible, faith in Christianity means that you do nothing else. Now I want you to think about that for a moment. When you picked up that favorite book and you began reading it, and you were engrossed in it and loving the characters, when you turned to the front cover to see who the author was, because maybe I want to read the next book, right? And I want to find who it is. When you looked at that author's name and you recognized who wrote it, did that stop you from buying the next book? Well, did that stop you from enjoying the character traits, looking deeper? Think about a classical art piece by Rembrandt or Monet. How amazing and beautiful, how they capture the light, how they blend the colors, how they take in a landscape for that one moment in time and capture it in its beauty. If I look at a Rembrandt or I look at a Monet and I recognize what they did and the fact that I couldn't do that, the fact of how much time and effort and how much just natural abilities they have. If I say that, does that stop me from appreciating it? Does it stop me from investigating it? What was Rembrandt's life like? Why is it that he did this particular style of artwork? Monet, right? The father of the Impressionist movement. Why is it that he developed and worked with and mastered that art form? Why is it that he painted over a dozen images of hay bales? A hay bale in a field. He painted that over a dozen times. Why? Can I investigate? Can I go further? Very likely you came today and you have some form of electronic device. That electronic device allows you to be connected with your friends, with your family. You can call, you can text, you can send emails, you can look things up on Facebook, you can go to the internet. Take that electronic device and flip it over. Does it have a name on it? Is that name your name? No. Is that name the name of a company? Well, yes. There's a host of companies, right, that make all of these devices. If you say, this is a fabulous device, does exactly what I want. Oh, wait a second. It's made by Apple. It's made by Samsung. I guess I can't investigate what the buttons do on it. I guess I can't actually use it and find out what the components are. I can't open it up and see the design that's in there. Absolutely not. You see, what we have is, we have a faith. But see, that faith is built on knowledge. And as a scientist, I can recognize, I can give an attribution to what is around me. And that in no way limits me from investigating, from digging deep, from seeing how we are composed, how the processes in our body or in nature or in gravity or in our solar system, how they operate, how they move, what they do. In no way does saying that God did it stop me from seeing how it functions and why. That's an important aspect as we move into the idea of evaluating the Big Bang. And we're going to do it in light of, for a few moments, a biblical comparison. We're going to look at the origin sequences that we find in the Bible with the origin sequences that the Big Bang lays out. We're also going to look at the internal inconsistencies and the external inconsistencies with the Big Bang. First off, what does the Bible say? The Bible gives us a creation account, and it lists days, all right? Day 1, the heavens, the earth, light was formed. Day 2, we have the waters and the expanse. We have day 3. Day 4, the sun, moon, and stars. Day 5, birds and fish. And then day 6, man and animal life came along. When we look at the Big Bang, the sequence is completely different. Okay, so right off that tells us that these are two different, distinct, separate descriptions, models for the origin of our universe. That's an important fact because in many times, and many people begin to merge the two. And what that does is essentially you have to compromise on both sides because of the distinctness, the separateness, the individuality. You have to compromise on both sides to blend them together. Here we see that within the first second, the Big Bang talks about a singularity. Very hot, very dense. Within just a matter of microseconds, according to the model, you had the expansion into space-time. After 200 million years, you had the first stars and galaxies begin to coalesce, begin to form, begin to start their life cycle. And then it's 9.2 billion years into the process when we find that our sun and our earth and our solar system begin to take their shape. Oceans don't appear until 10 billion years after the origin. And then fish and birds and animal life following much, much after that. So you see that there's a vast distinction between them in their time scales. Focusing specifically on the Big Bang, I've divided it into sort of these 5 stages. We have the stage of the singularity, right, within that first second which I just described. We have the stage of expansion. We have a stage of inflation. A stage of thermalization, okay, so sort of the idea of heat and energy coming into some sort of equilibrium or traversing across itself. And then we have structure formation. And so what I want to do is look at this sequence in a kind of a close detail. We're going to evaluate it from a scientific perspective to see, does it hold up to, 1, science itself, and then also 2, does it hold up even within the construct of its own model? Here is an image, just a very broad overview of the timeline that the Big Bang lays out. And what you see is there on the left-hand side, you have that origin point, the singularity. There's a period of expansion. There's a period where it rapidly, the term used, inflates to a very, very large size. And then after that, you had all of the subatomic particles, right? Protons, electrons, neutrons. You had atoms beginning to combine and to form. And then at some point, a couple 100,000 years, the universe becomes what they say transparent. And all that means is that it allows now for the photons to travel unimpeded. Before that, they say that there are so many particles, it's so dense, the photons are being absorbed and re-emitted and reabsorbed and re-emitted. And so after 300,000 years, you had this point when now the photons can travel through the space-time. And then following after that, you had the formation of various structures. So we're going to break up the science discussion, evaluating the Big Bang in these two categories. Internal inconsistencies, all right? So that's conflicts within the model itself. What does the model say in terms of its own scientific standing, its own scientific description? And is that consistent within itself? Not really looking at outside, but just in the pathways that it describes, in the processes that it lays out. Does it meet and match and follow the scientific laws and principles that we know do exist? And then the second area is looking at the external inconsistencies. With just the observations that we make, that we have, that we can glean and collect, how do you get from the beginning to now? Is that consistent when we place those observations back onto the model? First off, in our internal inconsistencies, we're going to look at the idea of the fact that it's not purely physical. And that's a very important point to consider, because the Big Bang is the naturalistic, the physical description and mechanism. It's designed that it is only using that. It's not supernatural. You're not bringing God into it. In and of itself, it is supposed to describe everything that is seen and everything that proceeded from that origin point. The second type of internal consistency is the idea of using unknowns and unknown processes to turn around and describe unknown processes. You see, there's a circular reasoning to that. And so we're going to talk about and illuminate some of those unknowns on top of unknowns on top of unknowns. Purely physical. I have placed on the screen there a quote by a physicist, George Ellis. Read this quote with me. People need to be aware that there is a range of models that could explain the observations. For instance, I can construct you a spherically symmetrical universe with Earth at its center, and you cannot disprove it based on observations. You can only exclude it on philosophical grounds. In my view, there is absolutely nothing wrong in that. What I want to bring into the open is the fact that we are using philosophical criteria in choosing our models. A lot of cosmology tries to hide that. All right, so I placed the first part of that quote on the screen. And I want you to notice that what he says is, if you take the observations and you construct a model, he said there's lots of models that could fit. And he even throws one out. He says, if you construct a model of the entire universe and it's spherically symmetric and the Earth is at its center, he said, by observation, I can't disprove that. But then the second part of that quote, he says you can only exclude it on philosophical grounds. Okay, we'll think about that for a moment. He says it's not the observations. When we look at a spherically symmetric universe, or we look at the universe that the Big Bang describes and the shape and the construct that it has, he says you can only choose between the two, not based on observations, but based on philosophical grounds. And then he says, well, I want to bring into the open is the fact that we are using these philosophical criteria in choosing our models. A lot of cosmology tries to hide that. What this is saying is that the choice that is made, choosing the Big Bang, is not a choice based on prior observations, looking at the model and developing it to match. He says there's multiple models. I can't disprove any of them, but this one philosophically meets the desire, the expectation. That's very important because it takes the Big Bang out of the naturalistic, physical mechanisms that it describes itself, and it says, well, we're using natural mechanisms, but we're just choosing that model because we like it better. That's important. Evolution, and in this case specifically the Big Bang, is a philosophical belief, and as that, dare we say, it's a religious choice. Okay, now it's not a religion that we might think about that is based on a text such as the Bible, with a God or a being that is above, that is looked at or is worshipped, but it is a belief system. It is something that is chosen not based on observations, according to George Ellis, but based on philosophical grounds. Well, that's religious in nature and constructed that way. For those that say that evolution is science and that the creation model, the creation worldview is merely religion and is not science, that's false. It's not. One is science and one is not. In this case, we have criteria and we have to match it scientifically. We have to match it with our observations and develop our models that proceed from that. The second area, the type of internal inconsistency, is the idea of unknowns explaining unknowns. In science, unknowns are critical to developing good models, developing a hypothesis, testing that hypothesis, seeing if it's correct or not, right? There's always, we're trying to push the boundary in science of what we know and what we don't know. And so unknowns play a crucial role, a vital role, a very important role. Unknowns are good, except in the case where an unknown, okay, it's there, you don't know what it is, you should try and test it, you're looking at it, trying to define it and describe it, but wait a second. You have another unknown, and you begin to take one thing that you really don't know, it's not really well defined, and you begin to say, that's true, this is good, this is fact, and I'm going to use it to describe something else. Well, you can't describe it yet until you clear up what this is. And now there's oftentimes that there's multiple unknowns and you're working towards each one. But when unknowns become dependent on other unknowns, then you're leaving behind the observations that are needed. One case in point, which we'll talk about just a little bit because it comes in several steps in our discussion. Right now, the universe, okay, according to the Big Bang, according to many astrophysicists, is described in sort of three components. Those components are matter, atoms, right? What you're made of and what I'm made of, what our moon and our earth and our sun and our solar system, what the nebula, what the galaxies, what we see, what we measure, what we test, right? Atoms. Two other components that are more recent additions into the model: dark matter and dark energy. Now, is it true that at times we have looked into scientifically different things, into the microscopic or into the macroscopic, and there have been things that we didn't see at one point and we saw later? Well, absolutely. The electron, the proton, the internal components of the atom, absolutely. Things very distant, okay? Galaxies and planetary nebulae and things like that, absolutely. Okay? Dark matter sits at sort of this interesting boundary, okay? It's this unknown, it's something that is not seen, that's where the name comes from, dark, okay? We're not seeing it, it's not visible, we're not observing it. But then it's matter because it's supposed to influence in some way, gravitationally, what is out in space, okay? Now, going back, the idea that there is matter in the universe, or matter actually in specific objects, say galaxies, that we are not seeing, but are having a vital impact and an influence. That's been there for decades and decades. Okay, that's great. because as we get better with our techniques and we look deeper and we look more, we can begin to find it and to isolate it. The problem is, in dark matter's case specifically, is that it has become sort of attached to and appended on a whole host of unknowns. Okay, so it's an unknown all in its own. We can look at it and research it and try to discover it. But then to take it and to say we're going to apply it into this area, larger and larger, and that now, at this point in time, you see on the pie chart, right? 24% of our entire universe is made up by this matter, okay, which has mass, which has gravity, gravitational influences, 24% of it within our universe. Okay, the other component to that is dark energy, which is vastly different and vastly, less known, less any observations connected to it. Dark matter does have a few observations, and those observations are always in localities. Okay, so we're going to talk about how they have taken this small unknown, looked at and researched and grappled with, and they have applied it to the entire universe and its development. And we'll see how that is not an extension that can be made. Here we have a quote at the bottom underneath that pie chart. This quote comes from the Jet Propulsion Laboratory, an extension of NASA. They have an educational site, right? So this is an educational. They're giving you a nice synopsis of things that are known and not known. And here is what they say. It says, "It is also an uneasy feeling that the majority of stuff in our universe is composed of matter and energy that we can't see and have no idea what it is." Okay, an uneasy feeling. Well, that uneasiness is because of the scientific and the observations. Okay, so kind of nagging there in the back is the fact that when we look at stuff and we research stuff, it needs to connect with observations and reality. There's this uneasiness because there is this huge disconnect between what is looked at and what is developed into this theory, composed of matter and energy that we can't see. So we'll watch for these inconsistencies, both internal and external, as we work through some of the stages of the Big Bang. All right? The very first stage, which we talked about initially, was the singularity. Okay? Now, discussing what came before the singularity is a huge question, which we have looked at various points in other lessons. We're going to focus on, at this point, just the idea of the very beginning, not necessarily maybe where it came from at this moment, all the matter, but what about the singularity itself? Its origination, but also, what is it? Why is it dense and not a vacuum? All right, so first off, this is not a purely physical idea. The concept of a singularity in scientific terms is defined as a point at which a function takes an infinite value. All right, so the definition of a singularity places it in the realm of infinity, a non-measurable entity. Physical values do not exist. All right, so singularity is a mathematical concept, sort of a discontinuity. If you have a nice continuous or smooth function, a singularity is a discontinuity in that function. And so it's a point that has no size, it has no dimensions to it. That is the definition of a singularity. It's infinite. It's not a measured finite value. And so placing that as the initial condition of the Big Bang at that point takes it out of being a physical description. In addition, though, added on top of that is the idea that, well, okay, this singularity is dense, okay, right? Because at the origin of the Big Bang, it had to contain all of the matter that would then populate our universe, all right? So incredibly dense. But the question comes, why dense? If it's a singularity, why can it not be without density or sort of in a vacuum idea? Here is a quote from Stephen Hawking. He says, "At this time, the Big Bang, all the matter in the universe would have been on top of itself. The density would have been infinite. It would have been what is called a singularity, and notice what he says there at the end. At a singularity, all the laws of physics would have broken down. All right, so Stephen Hawking, right, who has contributed vastly to the Big Bang cosmology at different stages and in different ways, he says at the beginning, at this singularity where all the matter has to be on top of itself and in this unmeasurable, infinite state, he says all the physical laws have broken down. Well, what does that tell us about its physical condition? It means that it's not physical. It is a non-physical. It is a philosophical choice, using Dr. Ellis's words. How then, if he says all the laws of physics would have broken down, how then can we know? How then can we know that the singularity contained all the matter or was infinitely dense, right? We use the laws of physics to define and to describe and to measure. How can I know how much something weighs? How can I know how much matter or mass is in an entity? How can I know what sort of gravity it has, or what sort of heat it has, temperature, density? All of these things depend on the physical laws to measure them, to describe them. And so if you take out all the physical laws, then you can't tell me how much it weighs, or how dense it is, or how hot it had to begin. Could the singularity have been infinitely vacuous? Well, in this model, you couldn't tell me that, yes or no. Stage 2 of the Big Bang is the idea of expansion, all right? So given that the singularity is there, their model says that it began to expand. Well, the initial question is why? Why expansion? Why not contraction? Why did it have to move? We're not asking the question what caused it at this point. We're just asking the question of why expansion itself. You think about something that is infinitely dense, or you think about something that has extreme density. Well, physical laws tell us that that is a case of contraction. The Big Bang will need that contracting process from gravity and mass much later in its sequence if it's going to generate all of the structures we observe. But at this stage, they need the opposite to happen. Sometimes people will throw out the idea of inflation, and we're about to talk about that. But inflation is not the reason for the initial expansion, because inflation is a period that begins and ends. So expansion itself does not follow simply from the physical laws. Again, the singularity had no physical laws, so the reason why it expanded and didn't contract, you can't say. You can't describe that. It is not a purely physical description. Third, the inflationary period. All right, so this idea of inflation, it means that the singularity was beginning to expand. But you see, we live in an enormous universe. So you got to get from an infinitely small, right, a singularity, a single point, all the way to the vast universe that we live in. You got to do that. And according to them, you have 13.7, 13.8 billion years to do that. Well, even in their model, that is not enough time to get from the starting condition to what we see today. And so the idea of inflation was proposed and put forward in the 1980s to try and account for this, or try to put something in, because the standard Big Bang cosmology absolutely didn't work, even from that expanding point to what we see today. But the question, again, it needs to be asked, why inflation? Why did it begin, and why did it stop? Now, this falls into sort of two of our categories. We're using an unknown to explain an unknown, all right? So we're using expansion, but we need to expand really, really rapidly. But that's an unknown. And so we throw in what is called an inflaton field, which is where we get the inflation idea. So here is this physical field that we need to exist. We don't know anything about it. We don't know where it is or why it is. We don't know why it started or why it stopped, but we really need it because we have this other unknown over here of how we move from small size to big size, trying to match our observations. But again, inflation is this starting and stopping. On this chart, okay, at the very far left end, you see the words Big Bang there in black. Moving into that sort of expanding zone, there's a little bracket, okay, and a little word that says inflation, and that is showing you this very, very rapid increase in size, but it had to have a starting point and a stopping point with no physical mechanism to generate either one of those. That's the third stage. Literally, we have not even got to the first 1 second of the universe's existence in the Big Bang. And we still do not have a mechanism to get from one stage to the next past the first second. When we now change gears just a little bit and we say, okay, there are these internal inconsistencies, these problems that arise. We have external inconsistencies on top of that. We have observations today. How do those observations, when laid back into the Big Bang cosmology, how do they help us? How does it hurt us? How does it take the Big Bang and its construction? First, we have what is called the horizon problem. Now, oftentimes for creationists, for those who believe in a young universe, okay, a time frame not of billions of years, the question is, well, there's this light travel problem. Well, the Big Bang has a light travel problem as well. You see, we have this enormous, vast universe, and to get from small to large, we have to do that. But there's this observation called the cosmic microwave background. And the cosmic microwave background is a measurement of microwave radiation, which in the Big Bang cosmology is believed to be the remnant when the universe became transparent and the photons were then able to traverse space sort of unimpeded. But the cosmic microwave background has this property that when you look in different directions, the relative intensities are the same. But yet this background radiation, according to the Big Bang, is supposed to be equal across the entire sort of volume that the Big Bang proceeded to develop. Well, the problem is that there was not enough time, even in the Big Bang, for that thermalization, for that evening out, for that leveling of all the radiation in this region, for that to happen. In trying to deal with this substantial problem is where the idea of inflation began. Okay, maybe it thermalized really quick, and then after it thermalized, after it got there, we then can initiate and push this inflation and have the universe that we see today. This is actually a picture of the radiation that is from the cosmic microwave background. What you see is across the very middle section is all the microwave radiation that comes from our Milky Way galaxy. So if we ignore that or we try to remove that out, then we have the rest of the sky. Now, this is a little bit misleading image. It's the image that you typically see when you research this. It's a little bit misleading because the scale is within 1 degree Kelvin, okay, actually micro Kelvin. And so the blue and the red are really only a micro degree apart from each other. And so it is a very smooth in its intensity level. But how did that happen? This is the observation. This is the measurement. We then apply it to the model and we have this time element that does not fit. How does it have an approximately uniform temperature across its entire universe if it is a remnant? That is the question that remains unanswered and not answerable in the current Big Bang cosmology. We see that the microwave background falls sort of after that red disk in this image there, sort of in the middle. That is the point when that radiation began to emanate. The next major external inconsistency is that of matter and antimatter. Now, the first question is, you might have heard that term antimatter, right? A lot of science fiction shows talk about it, maybe Star Trek or something like that. Antimatter is sort of this a little bit misleading term because antimatter is matter. It is just sort of an opposite charge or an opposite sign to the normal, usual counterpart. And we see that in the idea of an electron. An electron is a subatomic particle inside an atom that has a negative charge. The antimatter, or the opposite, which has the same mass and the same characteristics except that it has a positive charge, is called a positron. Okay, not a proton, but a positron. So you have this electron and you have this positron. You also have a proton and an antiproton. You have neutrinos and antineutrinos. It's not some sort of science fiction thing. They're real particles with real mass that really do travel and have their own characteristics. Now, the question is, though, that in the initial production that the Big Bang describes, all of the physical processes that tell us how matter and antimatter interact, how they change forms into energy and matter, tell us that they do this in equal abundances. Okay? So over in Europe, right, there's CERN, or the Large Hadron Collider. Okay? You have these particle accelerators that are taking these small subatomic particles and getting them up to high speeds, slamming them into other atoms to see what comes out. It's a beautiful science because it follows conservation laws. What they put into the system has to be accounted for by what comes out of the system. And we see that there's these matter and antimatter that is produced in these occasions. And so what we say is, okay, well, when we think about the Big Bang, where is the antimatter? You see, because in our universe, it is dominated by usual, regular matter. Antimatter's there, but it is extremely minor. What we see here's a quote from CERN, the high-energy particle physicists, okay, that run these colliders. They say the Big Bang should have created equal amounts of matter and antimatter in the universe. Based on every law and principle that we know, that we function at, and we do repeatable science right now, there should be equal abundances of these two. What are the observations? They go on to say, but today everything we see, from the smallest life forms on Earth to the largest stellar objects, is made almost entirely of matter. Comparatively, there is not much antimatter to be found. This asymmetry, right, the unbalance between matter and antimatter, is a huge problem for the processes described in the Big Bang. Okay? This is observation. Matter and antimatter. It's production and exchange with energy, right? We have the equation that Einstein, E equals mc squared, the fact that matter and energy, okay, you don't create or destroy either one, but they can change forms between each other. You smash a high energy proton or electron or helium nucleus into other matter, you will get forms of energy, gamma rays, X-rays, neutrinos, various particles on the other side. If that's the physical processes, if that's the observation, where is that remnant in the Big Bang? One of the last external inconsistencies I wanted to talk about is the structure formation problem. The Big Bang assumes a homogeneous and isotropic universe. Big words, all they mean is that homogeneous. If you're in different locations, the universe should look the same. If you're in one location but looking in different directions, the universe should look the same. The uniformity, though, of the cosmic microwave background is often used to justify these parameters. The problem is you need a mechanism to transition from this homogeneous, this isotropic universe into what we see today. When you think about the universe, what are the objects or the imagery that you see in your mind? You see these beautiful star clusters. You see these planets, you see these amazing galaxies, right? These large-scale structures, okay? Even galaxies form sort of clusters of other galaxies and superclusters. And so you have all of this structure, but how do you get from smoothness and evenness and isotropic viewpoint to what we see in all of the structure formation? Here is an image called the Hubble Ultra Deep Field. It was an image taken by the Hubble Space Telescope of a small patch of sky, very small, that didn't have any observable known objects or entities in that direction. And so if we sit at and we stare at it for 1 million seconds, 2 million seconds, what could we find? What would be there? And what do they find? They find this. Full, practically every illuminated object on that image is another galaxy, potentially even another group of galaxies. The structure we find in our universe is amazing, very prolific, very abundant, but you got to have a mechanism to form it. And I mentioned earlier about the idea of, okay, well, matter can coalesce, right? Gravity pulls inward, right? It's an inward force. It's something that grabs and contracts. Well, that's not what you told us at the very beginning, right? We needed expansion and we needed inflation, and now we need contraction from gravity. You see, the long, gradual process of forming galaxies, not only do we have to get from smoothness to the abundance of structures that we see today, but you got to do it really quick, okay? Because the deeper and deeper we look, the more structures we see. So in the Big Bang idea, the deeper you look, right, the more distant you look, you're looking back in time, and so at some point, you're looking back to the moments following the Big Bang. Well, what should you find? You should find no structures, or you should find structures that are very, very underdeveloped. They're not well developed and well formed. Okay? We're still looking deeper and deeper, and we're still finding formed structures. So whether you're adhering to the top-down galaxy evolution model or the bottom-up galaxy evolution model, you've got to do it fast. You've got to get these structures going, and that's not what we see and observe in a physical reality. In a concluding thought to our lessons, I want to focus on and think about just for a moment. When we look at the Bible, there is a consistency to creation. A consistency to the fact that the creation was by God. We see that what Moses wrote, right? Genesis 1 and 2 clearly talks about God's creation week, His setting things in motion, providing the context, providing the structure, providing the reasoning and the purpose. Genesis 1 and 2, right? So Moses wrote it. We turn to the Old Law, and the Old Law confirms what the history told us originally, right? Exodus 20, verse 11, in 6 days God created all that within the universe is. All right, but we also have the psalmist, right? The psalmist sang about God's creation, that by the Word of God it was created. In the beginning, God created it, that He established it, that He upholds it. We have in the New Testament, Mark 10, verse 6, right? In the beginning, God created them male and female. Jesus proclaimed God's creative abilities. And we turn to Romans and we see that Paul also preached that same consistency. For since the creation of the world, His invisible attributes are clearly seen, being perceived by the things that He made, so that they are without excuse. You see, we have what's around us. We have this structure, this development. We have this complexity. We have this design. We have this functionality. We have this purpose. If I, as Moses did, as the psalmist did, as Jesus did, as Paul did, if I attribute that to God, does that stop me from finding out about the moons of Saturn? Does that stop me from investigating why the Andromeda Galaxy has these satellite galaxies orbiting it? Why it's being drawn in and we're coming closer to it? Does that stop me from understanding how particle physics works? How there's antimatter and matter? Absolutely not. I can look at Monet and say, that is amazing. I can look at his individual brush strokes and see how he created and mixed his oils. I can look at the heavens and do the same. Monet did the art. God painted the heavens. It's amazing.
If these kinds of things are of interest to you, then we encourage you to go to our website at apologeticspress.org and look at the offerings that we have there available for free. We have other products that are available for purchase that we print or that we produce and sell DVDs and books and several other offerings there. If you have any specific questions that you might have for me or any of the people at Apologetics Press that might be relevant to, we encourage you to email us at mail@apologeticspress.org. Thank you very much for your attention.